Sarah Perrin to start things off, talking about generalization and meaningful games by learning master policies. Take it away.
So hi, I'm very happy to be here. This is kind of special for me because it's my first talk in person, because I started my PhD just before the pandemic. So I will talk about generalization in MFG games by learning master policies. So this is a recent work that have been accepted to AAA this year. This is joint work with Romuald Dely, Mathieu Geist, Mathieu Laurière, Julien Perrola, and Olivier Pietquin. Okay, so first, a very quick introduction about multi-agent reinforcement learning and MFG games. As you all know, multi-agent reinforcement learning and MFG games can be useful for a large number of applications, such as economic, crowd motions, traffic flow, etc. What is important is that in multi-agent reinforcement learning, often if we don't have a lot of agents, we can have like one policy per agent. But as the number of agents grows, this becomes intractable. So what we can do is make the mean field approximation and basically suppose that we have an infinite number of players. And if we also have the homogeneity and the symmetry assumptions, then we can just keep one policy for the representative player. This comes at the cost of dealing with the population distribution, which is the mean field term. But this still offers a simple representation, and it can be useful to approximate equilibrium in infinite games. So in this talk, I will suppose that I have a finite state and action spaces, X and A. We will be in a setting close to the finite horizon setting. In classic Markov decision process, so this is the framework of reinforcement learning when we have a single agent. We have transition probabilities, reward function, a total reward that depends on the policy or on the control. And the goal is to find an optimal policy. But now if we add min-fit games on top of that, we have this additional object, which is a distribution mu over the space of this distribution over state space. And all our objects now depends on the distribution mu, such as the transition probabilities, the reward function, the total reward. And now that we have this additional distribution, our goal is to find a Nash equilibrium. So what we will do, like to fix the distribution and to iteratively find a policy against this distribution. And at the end, we will get the Nash equilibrium. So I won't recall the definition of the Nash equilibrium. I guess a lot of you are familiar with this. And now I'm going to dig a bit into the main part of the paper. Is how we can go from classical policies to master policies. Our first, what we remarked was quite simple. When we solve a min-fit game, we really often have an initial distribution mu0 that is fixed. So this means that what we are going to do, so when we maximize the total expected reward J, it is always related to this given initial distribution. And basically, we have population agnostic policies, which are policies that doesn't depend on the distribution, but as we are in a finite horizon setting, so this is why we have this n, and we have the state of space X. This is problematic because as everything depends on mu0, of course, the Nash equilibrium also depends on mu0. So this is why we have still mu0 in the definition, and even the mean field flow that is generated by the policy, of course, will depend on mu0 because we start from mu0, and we will use the policy that have learned against this fixed mu0. Now, maybe this is not very problematic, but in fact, if we change mu0, we can't generalize at all because, of course, the policy won't be optimal anymore against another distribution. And this also is kind of weird from the machine learning perspective, because if we change mu0, nothing is right anymore, and the policy only depends on the state. So this means that it's like the policy is blind to the distribution, is blind to the other agents, and this is not very natural, like in multi-agent reinforcement learning. So this is why we had this idea, which is in fact quite simple. It's just we want to add the distribution to the state space. So this means just add the distribution to as an argument of the policy. So now we have a population-dependent policy, which we denote P tilde, and we still have a correspondence between the previous setup and the new one. We just input the distribution to the state of the policy. Okay, so now let me define what is a master policy. So master policy is a population-dependent policy that allows to recover a Nash equilibrium from any initial distribution. Of course, we don't think that this is always possible. Like, we probably need to have a unicity of the Nash equilibrium, because otherwise, especially from the learning perspective, a lot of problem can appear. But here we can still see the link between the previous population agnostic policies and the master policy. And what we prove in the paper is that if we have a Nash equilibrium from any initial distribution, then we can prove the existence of the master policy. So I'm going to try to present quickly the algorithm and some of our experiments. As I said, the goal is to be able to generalize, so to learn a policy that performs well on many initial distributions. And the idea is that now, if we have the distribution inside the state space, the agent, the representative agent, can see where are the other people. So at convergence, it knows how to react against any distribution. And our hope is that it generates enough various experience so that even if we don't see all the possible distributions over state space, because this is like very, very large, we would still be able to, if we have seen enough experience, to generalize well. So to do so, we use fictitious play. So this is an algorithm that we have seen, we have studied in a previous work. Basically, it alternates 3 steps. So an individual optimization, so we will compute the best response, then the population consistency, so this is just Fokker-Fleck equation. And what is very important is that we need to average all the distribution from the past. And this can be seen in the first step. We see that we compute the best response against this average past. And at the end, what is converging is the average of all the policies. So sorry, I don't have too much time to dig into this, but basically, the fictitious play algorithm is the step 1, 2, and 3 I just presented before. And now in this work, we add an additional layer of complexity because we need to do fictitious play against many different distributions. So we just add this loop over the different initial distribution. And then, so to learn the best response, we do deep learning at this step. If, let's say, our state space is a 2-dimensional state space, we can use a neural network and an algorithm like deep Q-learning to learn the best response. And what is very important is before we would only have this part of the network, and now we put a similar part here that represents the distribution. So the states X would be like a one-hot encoding in 2 dimensions, and the distribution would be like a histogram over the finished state space. I think I don't have too much time to present the experiments, but yeah, if, I'm happy to talk about it at the coffee break.
Okay, thank you, Sarah. Take maybe one quick question.
Yeah, sure. Here it's a simple game. So we have, I think, 16 over 16 states. We have different initial distributions. The goal for the agents is to go at the center of the domain and to spread a little bit, because there is this term in minus log of mu of x. And this term is like, we don't want to move too much. What we did is to learn against these different distributions and to see if it can generalize to new ones. So now if we test from these distributions, which are basically Gaussians located between the corners, this is what we get at the end. We had 2 metrics, the exploitability, which says if we are far from Nash equilibrium or not, and the Wasserstein distance, which say if the population, the mean field flow is close to the optimal one or not. If we start from this initial distribution, this is a simple game, so we can compute the exact best response with like tabular methods. And we see that if we use the best response that have learned against another initial distribution than this one, it will be like completely blind. It will do like completely nonsense, because this is what we would expect. But with the master policy, so this is not perfect, and we still need to improve the algorithm, but we see that the the agent still managed to go near the center of the domain.
Okay, then in the interest of staying on time, let's thank Sarah once again.